Chapter 9, Oxidative Addition and Reductive Elimination. In the previous chapter, we started to study the main reactions in organometallic chemistry. We talked about ligand addition, ligand dissociation, and ligand substitution. And to note that these types of reaction, the oxidation state of the metal center did not change. In this chapter, we will study the addition of a ligand on a metal center by changing the oxidation state of this metal by increasing the oxidation state of this metal, and this reaction is called oxidative addition. So oxidative addition looks similar to ligand addition, but the difference is that the oxidation state of the metal center will increase. The reductive elimination is the elimination of the ligand by changing also the oxidation state of the metal by reducing this oxidation state, and for this reason it's called reductive elimination. So the oxidation state is a general method for introducing a pair of anionic ligands A and B by breaking the bond AB. AB can be, for example, like H2 or CH3I. I choose these two types of substrate since H2 we don't have delta plus and delta minus sides, and in CH3I we have delta plus and delta minus sides. In the oxidative addition, we break the bond AB to form two new bonds, MA and MB, that are in cis position. This reaction is reversible. That means it takes place in two directions. So the reverse reaction of the oxidative addition is called reductive elimination, and we eliminate two ligands A and B to form a molecule A. The direction of the reaction of the equilibrium oxidative addition or reductive elimination can be favored according to specific conditions that will be studied in the next slides. For example, if M is rich in electron density, the reaction is favored in the direction of the oxidative addition. And if M is poor in electron density, the reaction is favored in the direction of reductive elimination. During the oxidation state, the oxidative addition, the oxidation state of M increased by +2. So another factor that affects the direction of the reaction in direction 1 or in direction 2 depends on the stability of the oxidation state of M. If the oxidation state of M before oxidative addition is more stable than after theoretical oxidative addition, so the oxidative addition would not take place. During the oxidative addition reaction, the oxidation state, the electronic count, and the coordination number all increase by 2 units during this reaction. So the oxidative addition is the change in the formal oxidation state of the metal M that gives rise to the oxidative and reductive part of the reaction names. During the oxidative addition, we have formation of two anionic ligands A and B on M from the molecule AB. This is due to the transferring of the two electrons from the metal center M to the bond AB. This is an example of a iridium complex where we add a hydrogen molecule. The first step is the transferring of two electrons from iridium to H2. So we'll have by theory the three centers bond, then the bond HH is broken and formation of two bonds metal H in cis position. So the oxidation state passed from iridium 1 to iridium 3. The oxidation state increased by 2. The coordination number increased by 2 because we add 2 hydrogen. And the electronic counting passed from 16 to 18, so it increased also by 2. What are the conditions of the oxidative addition? A metal or a complex can do an oxidative addition with a molecule that we call substrate if we have at least vacant 2 electron site on M, and the electronic configuration of the metal M should be at least D2, since during the oxidative addition, the oxidation state increased by 2. So if we have D2 before oxidative addition, it will become D0 after oxidative addition. So vacant site and electronic configuration at least D2. For complexes with 18 electrons, we don't have a vacant site. So if this complex would do oxidative addition reaction, it should first lose a ligand to produce a complex of 16 electrons that can undergo, therefore, the oxidative addition. The change in the oxidation state means that the starting metal complex of a given oxidation state must also have a stable oxidation state 2 units higher to undergo oxidative addition, and this new oxidation state should be more stable than the initial oxidation state of the metal M. Binuclear oxidative addition. This is a type of the oxidative addition that occurs on two metallic center, homometallic center or heterometallic center. So complexes with 2 or more adjacent metal atoms can also participate in oxidative addition reaction. Each metal center changes its oxidation state and its electronic counting and its coordination number only by 1 instead of 2 occurring in the normal oxidative addition with a single metal center. For example, the oxidative addition of the complex L and M with the substrate AB, 2 equivalent of the complex react with 1 equivalent of the molecule. So we obtain LNMA plus LNMB. So the oxidation state of each metal center and the electronic counting and the coordination number increase by +1. Another type of the binuclear oxidative addition is the reaction of AB with a complex with two metal centers, so it will give LNMA plus LNMB. This type of binuclear oxidative addition is known in the case of 17 electron complex or in the binuclear 18 electron complex with MM bond. Whatever is the mechanism, there is a net transfer of two electrons into the pi orbital of AB bond. In other words, the molecular orbitals of the bond AB, for example, supposing the bond order is equal to 1, when the electrons are transferred from the metal center to the molecular orbitals of AB, they will occupy the orbital pi star. So in this case, the bond order of AB will decrease, the bond is less stable, therefore we will break the bond AB and we make two new bonds MA and MB. What is the mechanism of the oxidative addition? The mechanism of the oxidative addition depends on the type of the substrate used AB. And we will discuss three types of AB. AB is non-electrophilic, AB is non-electrophilic intact, or AB is electrophilic. We will start by the non-electrophilic substrate. What is the meaning of non-electrophilic substrate? AB molecule is non-electrophilic. That means it does not contain a net delta plus and delta minus charge. So the difference of electronegativity between atoms A and B is very small, or is equal to 0 if A is the same type of B. The non-electrophilic substrate known in the oxidative addition are H2, CH bond, SiH, SH, BH, NH, SS, CC bonds. And if we look to the difference of electronegativity, we can deduce that the electronegativity difference is very small, except in the case of NH. Aside from hydrogen, all these bonds are considered non-reactive in this type of reaction. In the family of the non-electrophilic substrate, we consider only the reactive molecule hydrogen. What is the condition of this oxidative addition? It generally requires the presence of empty orbital on the metal center in order for them to pre-coordinate in this type of reaction. What is now the mechanism when the substrate is non-electrophilic? The mechanism is known as the concerted mechanism. The two electrons are first transferred from M to the bond AB. So first of all, we have associative reaction where we prepare a complex with sigma bond AB. So the incoming ligand first binds as sigma complex, and then these electrons will be transferred to the molecular orbitals of the bond AB. So we will have a breaking of this bond and formation of the bond MA and MB. So, in other words, The concerted mechanism is one step is the association of the molecule AB to the complex, and the second step is the breaking of the bond AB and the formation of MA and MB. To note, for some types of complexes, what we called intermediate LNM sigma bond AB can be stable, so the oxidative addition would not proceed, so the reaction form only this type of complex. The second type of substrate in the oxidative addition is the non-electrophilic intact. This is a molecule that contains in general a double or triple bond, and only one of the pi bond is broken, leaving the second sigma bond intact. For this reason, it's called non-electrophilic intact. And the condition for this type of oxidative addition, it needs the presence of empty orbital on the metal to receive the ligand added. Example of this type of non-electrophilic intact substrate are alkenes, alkynes, and oxygen. Consider, for example, the oxidative addition of alkyne on a platinum complex. First of all, this complex should have a vacant site, and this is the case. The second point in this mechanism, the electrons of platinum will attack the pi bond of alkene, and by conserving the second pi bond and the sigma bond. So we will obtain a platinum metalla cycle with double bond. So we have metallocyclopropene. The nature of the R groups affect this oxidative addition. As R groups are electron withdrawing groups, so they will pump their electron withdrawing ability in order to help the promote of the transfer of electrons from the metal to the ligand. So as R is electron withdrawing, it will favor the formation of the metallocyclopropene. The third type of substrate is the electrophilic substrate, for example, as CH3I or CH3X. So it contains electronegative atom and is good oxidizing agent and is considered to be reactive substrate. So the electrophilic substrate is the most reactive in the oxidative addition, and the mechanism of the oxidative addition with electrophilic substrate is different. The oxidative addition in this case does not require the presence of empty orbital, so this oxidative addition type is known for complexes of 18 electrons. Example of electrophilic substrate, for example, halogens, Cl2Br2I2, Rx, methyl halide, aryl halide, HX, oxygen. In case of the CH3Br, for example, we will have two anionic ligands, CH3- and Br-. If the complex is initially 16 electrons, so the two anionic ligand will be added to M, and we will have the formation of two metal bond M, CH3 and M, Br. But in case of complexes of 18 electrons, so one of these ligands will be added, which is the stronger donor. So what is the mechanism of the oxidative addition in case of the electrophilic substrate? First, in case of non-electrophilic or non-electrophilic intact substrate, the mechanism is the concerted pathway. Two electrons are transferred from M to the bond AB, so we will have intermediate M sigma bond AB. Then this electrons will pass to the orbital sigma star of AB, so the bond AB is broken and we have formation of MA and MB. In case of electrophilic substrate, the mechanism is the non-concerted pathway. The electrons of the metal will attack the positive pole of the bond AB and to release X minus. So as in this example, the addition of CH3Br to iridium, we have formation of iridium CH3 and Br minus is in the outer sphere of iridium, so Br minus in the system. If the iridium complex can receive this Br minus will be bound. And iridium in this case is iridium 3, 16 electrons, so it can receive Br minus and we have formation of iridium 3 complex with 18 electrons. The mechanism is found in the addition of methyl, allyl, acyl, and benzyl halides. As the metal M is more nucleophilic, this type of oxidative addition has greater reactivity. Suppose we add electrophilic substrate to a complex of 18 electrons. So only one of the two anionic ligands, usually the strongest binding, will end up coordinate to the metal unless a separate substitution reaction occurs. This is an example of the addition of HCl to Re complex. Two electrons will attack the positive pole and release Cl minus. So this is a complex from rhenium -1 to radium 1. This is a complex 18 electrons. So Cl minus could not be added to the inner sphere of Re complex. This reaction will lose a one ligand CO, so it will release a vacant site, but in this case, the hapticity change reaction is stronger than the addition of Cl minus. So we will have hapto change from hapto 1 to hapto 3 allyl and not the formation of rhenium Cl bond. So the oxidative addition involves oxidation, that means removal of electrons of the metal. As the metal is more electron rich, the oxidative addition is favored. The most reactive metal with a substrate for oxidative addition is when the metal center is rich in electrons. So it can have strongest donor ligand, fewest pi acceptor ligands, or most negative charge. Also remember that the non-electrophilic ligands and intact usually require the presence of empty orbital on M, so it's known for complex of 16 electrons or lower. And in case of the electrophilic ligand, the condition to have empty orbital is not needed. Oxidative addition are easy to identify if you electron count the metal complex. For example, when we count the metal complex from initial state to the final state, we can know if the oxidation state has been changed or not. When an oxidative addition reaction occurs, the metal will be oxidized, usually by 2 electrons. Example, if we start with a metal in the zero oxidation state D8, after the oxidative addition, the metal will be +2 oxidation state and the electronic configuration is D6. H2, Rx, and HSI are three of the most common substrates known that perform well the oxidative addition reaction in a catalytic cycle. Kinetic data for oxidative addition reaction of MxCOPr32. As the electron density on M increase, so the oxidative addition on this complex is favored. The more electron-rich the metal center, and this is due to better donating ligand, so the faster the oxidative addition reaction. Consider, for example, iridium Cl and iridium Br complexes containing phosphine, and we add substrate H2. We know that Br is more donor than Cl since Br is less electronegative. So the iridium Br center, the iridium center in case of iridium Br complex, is more rich in electrons, so the oxidative addition will be favored, and that we observed about the rate constant, the reaction is faster. So we have one exception, is the oxidative addition of CH3I with the iridium Cl Bri series of complexes. Cl is less donor than Br and less donor than I. So in this case, iridium Cl should have the lower rate constant since the oxidative addition is not favored in this case. But the experiment proved that the rate constant is the greatest in case of Cl. So here we have another factor that we did not consider really in our course in organometallic chemistry, which is the size or the radius of the ligand. As we know, Cl has lower radius than Br than I, so the electrons on iridium are clear in case of Cl, so they are better donating to the CH3I. For this reason, the oxidative addition is the most favored in case of iridium Cl complex. Oxidative coupling. Consider this reaction where we have a chromium center with 2 alkene ligands that is transformed to chromium with 2 alkyl ligands. So we pass from chromium 3 to chromium 5. So this is an oxidation. And since we add 2 ligands, so it can be noted that this is oxidative addition. But as we know, in the oxidative addition, the coordination number increase by 2, and this is not the case. And the electronic counting increase also by 2, and this is not the case. So this reaction is only an oxidation. It could not be noted oxidative addition. What happened in this type of reaction? We have two alkenes that are coupled to form metallocycle. So this is an oxidative coupling and not an oxidative addition. So chromium on the right has two anionic alkyl ligands forming a metallocyclopentane ring. We have done an oxidative addition only to say that we have oxidation. So this is not a pure OA. Forming a new bond between the two ethylene ligands and losing the double bond, so we have coupled the two ligands together, and the name is oxidative coupling. The driving force for this reaction is the formation of a new CC system, sigma bond, stronger than pi bond, and the creation of two new strongly donating anionic ligands. If we compare these ligands, we can say we have two alkyl, and here we have two alkene. So the bond, the chromium alkyl, is more stable than chromium alkene, since alkyl are more donor. So in thermodynamics, this reaction passes from less stable state to more stable state. Reductive elimination is the reverse of the oxidative addition, and it occurs in general in the higher oxidation state because the formal oxidation state of the metal is reduced by 2 units in the reaction. For a complex LNMAB, the reductive elimination will form LNM plus AB. To note that AB should be cis in cis position. So the oxidation state and the electronic counting and the coordination number were decreased by 2. When the ligand dissociation does not occur, that means the reductive elimination will be slow. For example, in case of complexes containing methyl and hydrogen, this complex structure are not common since the reduction elimination is favored to form CH4. So in this reaction, the reductive elimination of an alkane is usually in thermodynamics favored. A stable example of this type is the iridium hydrogen methyl Cl phosphine complex, where hydrogen and methyl are in cis position. For temperature greater than 100, this complex is unstable. It will lose directly the methyl and H by reductive elimination to form methane. Since electron-rich metal complexes favor the oxidative addition and the reductive elimination is the reverse of the oxidative addition, so the electron-poor metal complexes will favor the reductive elimination. As the metal center M is rich in electrons, the oxidative addition is favored. As this metal center is poor in electron, the reductive elimination is favored. And we know that a metal center is poor in electrons when it has electron withdrawing ligands, for example CO, or the charge is positive, cationic charge, or is not saturated, so it's 16 electrons or less. While reductive elimination can occur from saturated 18 electron complexes, the two ligands to reductively eliminate our cis position, it can be promoted by a ligand dissociation, generating unsaturated and more electron-poor metal center. For example, this is a complex of platinum 18 electrons, and we have CH3I. So by theory, the reductive elimination is possible in this case. But since this complex is 18 electrons, so rich in electrons, so the reductive elimination of CH3I is not favored. So we heat this complex to lose a ligand I-, which is weakly coordinating to platinum. In this case, we have platinum 4 with 16 electrons. So in this case, the reductive elimination might be possible.